So my name is Adam Thomas. I am heading up a small team called the Data Science and Sharing Team that is embedded within Peter Bannattini's fMRI core. Our mandate is to make open science work a little bit better within the NIMH intramural program. So I'm going to tell you a little bit about the world of data sharing and open science more broadly, about the problems that we're trying to address, what we're trying to do to address it, and how you can go about it. Right, and I have borrowed, adapted, or stolen a lot of material from the web from some of these good people: Ross Poldrak, Chris Korgolewski, Brian Nozak, Tal Yarkoni, Nico Kriegoskorta, Tom Nichols, Phil Bourne. There's a number of other people. The open source community is growing. They're very active. They're very active on social media, and as you might guess, they share their things. So proper credit to the bits that I've taken from them. Okay, so as I said, the brief outline of what I'm going to talk to you about today is why we need open science, or what problems we're trying to solve, what open science actually is and what it's doing, and how you can do it right here at the NIMH IRP. So first of all, why, or what is the problem? So the problem really has four parts, I like to say. One of them is reproducibility. This is just one of a lot of papers that you can see these days. This one's from Brian Nozak in 2015. He is plotting replication effect sizes against original effect sizes, and you can see that it's well below the intercept. So basically it's just a very quick way of looking at a lot of studies and saying that when you go to replicate them, you do not get the effect that the original authors reported. And I'm not going to spend a lot of time on this because there's a lot on this, and I'm assuming if you come to this talk, you probably heard this before. There's something we call the replication crisis. We've been talking about it since the Ioannidis paper of August of 2005. So 12 years we have been addressing this. We are moving forward, though. I'm going to talk about a little bit more of that in this section. The second problem is wasted time and resources. So there's a little informal poll that various people have done, and they ask scientific researchers, how much time do you spend handling, reorganizing, managing, sometimes people call it wrangling your data, as opposed to actually doing science, so actually applying the skills that you've been trained on, whether it's neuroscience or genetic science. I mean, there's just a whole lot of bookkeeping and housekeeping tasks. And the median answer is 80%. Amongst graduate students and postdocs. So that's kind of awful, right? There's a lot of things that we're training scientists to do that they don't have time to do because they're doing the bookkeeping. And we would like to address that. Also in the wasted time and resources category is the unpublished data. So the one that is most common is the file drawer problem. I'm sure you've heard of this. The idea is that some young scientist comes up with a brilliant hypothesis, they collect the data, they test it, it doesn't work out, so they toss the data into their file drawer and say, I'll get back to that data someday, and never do. And then it never gets published, and then another dozen young scientists test the exact same hypothesis, and we kind of end up wasting a lot of effort and resources on that. Second, lost staff and lost metadata. So this is the problem where a graduate student or a postdoc comes in and has some brilliant idea, collects a bunch of data, and then something changes. Maybe they change universities, maybe they move off to industry, and then that data that they collected or the analyses that they did end up on a hard drive or a flash drive somewhere, and then nobody's ever able to make any sense of it later. And again, that data and those resources are lost. Also underutilized data. So we have some very expensive machines, and we collect a whole brain's worth of data. A lot of people go in and they will collect structural, functional, diffusion, sometimes spectroscopy on a sample, but then when it comes down to their thesis time, they really only have time to analyze one of those modalities, or maybe they only have time to look at one particular question. And then the rest of that data, in which there are dozens of other questions that might be asked, never get asked. So that's another aspect of wasted resources. And third is sort of a lack of transparency and reproducibility. It makes it harder for us to sort of make more integrative conclusions about the brain and about mental health. And this is something that you will see if you ever take the time to go look at these blue ribbon panels. So every 5 to 7 years, the NIMH will commission a blue ribbon panel or some sort of external entity to come in and look at what we're doing and say, how can we be doing it better? And so this is the blue ribbon panel from 2008. It includes this quote: the blue ribbon panel proposes that the basic and clinical groups at NIMH IRP be linked more closely than is generally the case at universities. Linking basic and clinical teams of investigators may facilitate the translational goals of understanding disease mechanisms and developing novel therapies. So if you don't have open and reproducible methods, it's very hard for one group to understand what you did and to try to reproduce it. And this is not new. You can go back all the way back to 1975, and you will find very similar quotes. All of our funders and all of our regulating bodies want us to work more closely together. If we're going to do that, we need to build more transparency into our model. And just as an aside, you can find all of those reviews. The NIH library has done a great job of archiving them at the Wayback Machine, so you can look at each of these. And it is it's a little depressing to see how reoccurring the themes are. Fourth aspect of the problem is, and I hate to use the buzzword, the big data revolution. So this is an article from Phil Bourne, who was until recently the director of the Office of Data Science at NIH. And in this piece, they argue that organizing and accessing biomedical big data will require different business models. So it's a fundamentally different approach to the way most of us were trained to pursue neuroscience. Most of us showed up in a lab, we came up with a question, we maybe had an IRDA to start collecting, maybe 20, maybe 100 subjects, and then we analyzed the data. But we're talking about a lot more data now. So for example, the UK Biobanking Initiative made this really useful little video. I've stolen a few screen grabs of it. So they're suggesting that the typical study these days might be 125 subjects, or in this case, 125 brains. That's what you're seeing in the cube there. The UK Biobank is collecting 100,000 brains. They currently have 15,000. They're freely available to anybody. We're going to have it on the BioWolf soon. But if you're going to analyze data on that kind of scale, it's not your laptop anymore. It's not an Excel worksheet. It is a fundamentally different way of approaching data analysis that brings in a lot of principles from computer science and database engineering and whatnot. I'm not saying that everyone needs to become a database engineer, but you do need to learn an aspect of some of those principles. And we're not stopping at 100,000. President Obama has started the 1 million person health study. That does not currently include brain imaging, but it's kind of clear where the trend is going. And Phil Bourne likes to talk about the problem of exponential growth. So he sees this change happening very, very quickly. And they talk about this a lot in Silicon Valley in the tech industry, that these exponential change curves catch a lot of people flat-footed. So the examples that he includes are film versus digital. So the Kodak Kodak company basically went bankrupt because the way digital film became dominant so quickly. You can also see it with what Uber is doing to the taxi industry, and also with what 3D printing is about to do to the manufacturing industry. It seems to be changing slowly, and then suddenly everyone is doing it, and anyone who's left doing it the old way is out of business. So Phil Bourne is suggesting that biomedical scientists also need to be worried about this, that the change is happening very quickly. Okay, so those are the 4 problems that we're trying to address with the open science revolution. Reproducibility, wasted resources, a lack of transparency and integration, and our students, our trainees are ill-prepared to work with these very large data sets in a different way. All right, so what are we going to do about it? What is it that open science is going to offer to help us get at some of these problems? I'm going to steal a graph from a paper that was put out by Chris Gorgolewski and Russ Poldrack, and they see open science as having 3 main pillars: data, code, and papers. And let me just talk about each of those in turn. Data. So I think we all know what open data is, the idea of sharing the data that you collected. Now, if you would go back 10 years, it wasn't uncommon that people would just put it on their website. Just, you know, your lab has a website, you put a little public folder there, it's like, hey, you want to see our data? You can look at it there. The open science movement argues that that is not good enough. Data should be deposited in a public, community-recognized repository with a stable DOI, digital object identifier. So the problem is your lab might go away. You might get hit by a bus. Maybe your server's going to crash and there's not going to be any kind of backup. There are groups of people that have built repositories that have thought through all of the contingencies and have worked very, very hard to make sure that your data is going to be available in perpetuity. So that maybe 30, 50 years from now, when your lab is gone and you're gone, maybe there's some crucial question for your very rare data set that they may be able to ask down the line. The data repositories follow something called a FAIR principle, which is an acronym that stands for findable, accessible, interoperable, and reusable. And ideally, they should be deposited before publication. So the best way to do data sharing is to put the data into the repository as you collect it. Almost all of the repositories will give you an option of an embargo. So the data is in the repository, it's organized in the way that you collected it, you can continue your analysis, you can basically keep it private until you're ready to share it, but it is much, much easier to share it at the end when you're actually publishing the paper if you put it there first, as opposed to in the process of trying to publish it and deal with the reviews and whatnot, you're also dealing with all of the issues of getting it into the repository. So the recommendation from all of these repositories is to put it in there early. There are a number of community recognized repositories. There's more every day. There are a number of MRI specific repositories, including fMRI and now OpenNeuro, which we'll talk a little bit more about. Coins, FCP, Lonnie, Loris. I mean, you can Google any one of these terms and you can read more about them. The ones in white will accept pretty much all data. The ones in yellow are more focused on derived data, statistical maps, and things like that. But if you are not doing brain imaging, if you're doing some other kind of science that maybe you think isn't that appropriate or doesn't fit as well into one of these MRI-specific repositories, there are also other options, data agnostic repositories. They include Figshare, Dryad, Dataverse, the Open Science Framework, or even our very own NIMH Data Archive. Depending on what you're collecting, they may have suggestions for you, data dictionaries that will allow you to sort of match the data that you collected with the types so that your data can be aggregated across different studies. But it's also, if your data is so unique, a lot of these repositories will just take a zipped archive if it doesn't actually fit into any of those boxes. So it's always possible and it's always advisable to share your data no matter how unique and weird you think your study might be. OpenNeuro is actually a particularly exciting one. So this is from Chris Gorgolewski and Russ Poldrack out of Stanford. So OpenNeuro was just debuted at the Human Brain Mapping meeting last week. And what they are offering is if you upload your data, they have actually built an analysis framework. So that you can apply FreeServer to it, you can apply MRIQC to it, or there are a number of little apps. They call them BIDS apps, which we'll talk more about BIDS in a few minutes. But it actually provides you with a platform to analyze your data in very standard ways. And you can do that for free. You can log in with your Google ID. And the trade-off is that when you upload data there, they ask that after you put data there, that it can be shared within 18 months. So this is their way of incentivizing people, but providing them with very easy-to-use tools to encourage them to share their data. So this is live now. Anybody can use it. Currently, the analysis credits are free as well. So it'll actually do the analysis inside Amazon Web Services, and their funder, at least for the time being, is willing to pay for those credits as well. As it becomes more popular, that might not be true. You can also upload your own Amazon key and upload it on your own dime, analyze it on your own dime. But for now, there's an opportunity to do a lot of analyses for free, so it's worth looking into. We have shamelessly copied this repository. So the NIMH intramural program was also interested in having an internal repository, and Chris and Russ had built such a beautiful one and put it all up on GitHub that we simply cloned it and forked it. So we're calling ours the NIMH Intramural Data Sharing Repository with OpenNeuro, or NIDO. It is, I think you can access that currently from an NIH IP. We have Javier Gonzalez Castillo's data up here, his 100-run study. We will soon be debuting this more widely. But currently there's just a couple data sets there, so be listening for more information about this one. Okay, so that's open data. Let's talk a little bit more about open code. Open code is the code is obviously how you analyze the data, what you did to get from the raw data to the finished product. And opening it up ensures greater reproducibility, and it includes the non-code methods, like if you're doing a wet lab or the aspects of how you actually collected that. All of that should be documented as carefully as possible so that someone can reproduce the study as precisely as possible. The idea of open code is to prevent reinvention. A lot of us are doing the same things over and over again, and we're writing new scripts to do to do things that have already been done. And a lot of people with computer science training, I've seen this a number of times, that people who didn't go through a computer science degree, who didn't learn about database principles, can sort of reinvent them as they're writing their MATLAB code. But if you do spend a little bit of time of searching, you can actually find very useful tools to do the thing that you might have decided to write the script for. So it allows you to download and improve on existing work. And there are great tools to make this possible called version control tools. There's two websites that are kind of dominating the field right now. One is GitHub, and the other one is Bitbucket. They both predominantly use a version control system called Git. And version control gives you many advantages to develop and open your code. First of all, it stores all your analysis in a central repository. And again, that can be private or that can be open, but it prevents you from losing your laptop, accidentally formatting your hard drive, or deleting things. It's always going to be someplace where you can get back to it. It also keeps a history of snapshots of your evolving analysis. So as you develop your code, you can do what they call check-ins and say, okay, I've got this working, and then you can check that in. And if at some point you decide that you've taken a wrong turn, you can fall back to where you were last Friday, and you can develop from there. It also allows you to switch between different versions of your analysis. So you may have been working on some code base and you thought, well, maybe I want to change the smoothing kernel, or maybe I want to explore doing this with Civet instead of FreeServer. There's a lot of branching points in our analyses, and what Git allows you to do is set up separate branches. So you can sort of chase that branch, and then if you decide that, no, that was a bad decision, you can come back to that branching point, and then you can go off in a different direction. So you build this tree of your analysis that is relatively easy to navigate. It also makes it very easy to adopt and modify code from other scientists. So if you get on github.com, you will find thousands, if not millions, of code bases from scientists and everyone all over the world. And you can download the exact code, you can get compilation instructions, and you can see how they got there. You can also do something called forking. So if you fork the code, then you basically create a copy of it in your own workspace, and then you can adopt it. And if you decide that if you find an error, or if you find something that can be improved on the code, you can then do something called a pull request, and which basically sends a message back to the original author and says, hey, I think that you could change this particular bit of instructions to make it a little bit clearer. Why don't you incorporate this into the main code? And then with a very intuitive interface, they can very quickly look at it and say, oh yeah, that makes sense. Or there can be a dialogue. It's like, oh, well, I agree with you, but maybe this should happen as well. So it provides this wonderful infrastructure for you to do communal science. And everyone can be looking at the same code base, and they can move forward more easily that way. Collaborate. You can also, so you can do this with strange scientists, and you can just randomly find a code, or find someone out there. But if there's someone at another institution, or maybe even in your own institution, and you are developing a code base together, Git allows you the ability to sort of do that simultaneously, and it will make sure that you don't step on each other's toes. Like, so if you're working on one function and they're working on a different script, when you both commit it to the central repository, if you have done something that is conflicting, or you're editing the same line, Git will say there's a conflict here, and you should manage it. Okay, open papers. So open papers includes a number of things. The most obvious one is preprint posting, which is becoming more and more common now. There's also open access and open review. I'm going to talk about each of those. But first of all, preprint posting. So the main preprint posting sites, the original one is arXiv, which is spelled counterintuitively ARXIV. So this has existed in the mathematics and physics and sort of quantitative science community since the 90s. It has been their practice for the past 20 years or so that as soon as they had a work that was near complete, they would turn it into a manuscript. They would upload it to this website. They might email some of their friends, or they would just let people know, it's like, hey, what do you think? There was no publisher, there was no editor, there was no peer review, and then a conversation would happen about the manuscript, and it might get changed, it might get retracted altogether, but there sort of is a totally open and transparent dialogue between the scientist about what makes sense and what doesn't. And then sometime later, it would eventually find its way into an actual sort of printed peer-reviewed journal. And this has been their practice for 20 years, but it's only relatively recently that the biomedical scientist, and just in the past year, pretty much every branch of science is now looking at the same model. So bioRxiv was one of the sort of clones of arXiv. It's a little bit more feature-filled. And again, it's the exact same thing. I mean, a lot of people find it crazy because people are worried about being scooped or their ideas being stolen. But The practice has demonstrated that that's not so much of an issue. You can put your ideas and your work right out there for conversation, and then after you've sort of had a back and forth about it, then you can send it off to a peer-reviewed journal. So the benefits include open access. There's no paywalls, so that anybody in the world can immediately see your work, regardless of whether they're at a wealthy institution or not. You can catch errors, so a lot of other scientists may find something, some problem with your code, and they'll let you know before it is properly in a printed publication. And there's a culture changing, right? So it used to be that people would want to hide their errors. If they made a mistake, they didn't want to get caught. But the open science community likes to try to remind people that we all make mistakes. These are extremely complicated analyses, extremely complicated code. It is not unusual for there to be errors in there. And some of the most famous people in the world have made mistakes. And it's much better that we get them out there and we get them corrected rather than just trying to brush them under the rug. Earlier citation. So again, the scooping concern. People don't want to do this because they're worried that they're going to be scooped. So as soon as you put a publication on bioRxiv, it generates a DOI, and more importantly, it generates a timestamp. As soon as that it is in the public sphere, it demonstrates that you have done that work from that point. And any reviewer who is reviewing a paper that might be similar to your work or might be trying to copy your work can then say, you need to cite this paper that's on this preprint server because this work is already pre-existing. Again, earlier precedent, it actually prevents the scooping. So Nico Kriegeskorda has a really great blog post. It's over here on the side. You can dig it up. I'll post these slides online, where he tells this great story about where he was working on a problem that he knew his competitors were working on as well. And so they were both running a very similar experiment, and they put it on a preprint server, and he had sent his to a peer-reviewed journal. And so while it was being reviewed, they got the reviewers back, and the reviewers said, you need to cite this other paper, right? So in the citation hierarchy, it appeared that they were the second ones to do it, even though they were simultaneous. So it's not so important to get, Nature 2017. You need to demonstrate that you had it out there and get cited before. That is the way to win that particular game. Right, and it gets your ideas out there sooner, and it actually improves the final submission. And so all of the journals that I have ever spoke with said that they are very happy to take papers that were previously on preprint servers. There was also an idea in the biomedical science community that journals won't accept something if it's been published somewhere before. This is not the case for preprint servers, and I have yet to find a journal that says otherwise. There is a website it's not on the slides, but I'll put it on the I'll put a link, make a link available that actually lists the preprint policies of every journal, and all of the major journals are now accepting papers that had been on preprint servers previously. Remember what I was saying about exponential curves? It is shocking how quickly this is happening. So if you go back to, I know it's a bit small for you to read, that's 2013. That's November of 2013, and the number is 40. There were 40 publications submitted to bioRxiv in November of 2013. Now, we're at, I can't even read it myself, I believe it's 12,000. So this change is happening very, very rapidly. There was a meeting of the BD2K initiative last December, in which Francis Collins and Harold Varmus sat down for an informal chat, and they said, oh yeah, all my postdocs, every paper, straight to the preprint server first. This is the current and former head of the NIH. So this has gone from a crazy fringe idea to totally mainstream in about a year and a half. So again, exponential change. Open access, this is a simple graph that says that if your paper is open access, it's going to get cited more. That it is in your interest to make your paper as accessible to the entire scientific community as widely as possible. Open review. So this is another slightly more controversial idea that maybe you shouldn't actually have a private review with the reviewers. That there's this idea that conversation between you and your reviewers could also be done openly on the internet. Now, there's also the question of whether or not it's anonymous. You can actually have an open review and still not reveal your name. There are perfectly legitimate scientific situations in which you can't say who you are. But the suggestion is that if it's an open review, that it is a more rigorous review. And people know that some other people are going to be reading their words rather than just the author, that they are a little bit more careful with them. I think we have all at some point experienced a sloppy review. If you haven't yet, you will. So the open review movement suggests that we can decrease the number of sloppy reviews, and if there is a sloppy or biased or careless review, that there will be an opportunity for other people to weigh in and say, hey, this doesn't make sense. So these are two websites that enable this: PubPeer and the Winnower. Again, this is a rapidly moving space, so there's other places that this can happen. So Nico Kriegoskorta, again, is a big advocate of this. So as soon as he's asked to review a paper, he sends an email to the author and says, hey, I've been asked to review your paper. I would like to do it on my blog. Can you post it on a preprint server, please, so that we can all have a conversation about this? And that is the only way he does reviews anymore. This has not been adopted as rapidly as the preprint servers, but it's a very interesting idea. Again, public discussion of pros and cons with submissions. You have the option of anonymity. It prevents low quality and or biased reviews. And then a last bit is to incentivize this stuff. So this is something that's been coming up more. So it's been embraced by the psychology community. Interestingly, the psychology community is a little bit ahead of biomedical sciences on trying to address the reproducibility problem. They have gone through a lot of work where they've gone back and looked at some really established scientific dogma, like psychological principles that everybody thought were true. And when they did it in sort of a double-blind, randomized control trial kind of way, a lot of them turned out not to be. And the field is kind of doing a lot of hand-wringing right now. So they're advancing some of this stuff more quickly. So this is a Psychological Review adopted this policy that every paper that went in, if they used open data, or if they used open materials, or if they pre-registered their paper, then they would get this little badge at the top of their paper, so they would just acknowledge that that's what they did. And it was just really rapidly adopted. The amount of it was just giving people a gold star and recognizing them for doing this was enough to sort of push people in that direction. So the community wants to go this way. It is a little bit more work, so we just need to give them reasons to do it. And I didn't talk much about pre-registration, but that is the idea that you actually go to a journal and say, this is the study I'm going to do, before you do it. And that sort of prevents you from changing the hypotheses or changing the studies halfway through, which I think we've all been tempted to do at some point. Okay, last bit. How do I do open science? How do I adopt these principles, specifically here at the NIMH IRP? So one of the most important things is to plan ahead. You can't sort of make it up as you go along. And if you want to share your data, you do need to get consent from your subjects to share the data. The field, again, has changed rapidly in this respect. There was a period of time when the data could really only be used for the original experiment. You're seeing that change all over the place. Now, within the IRP, if you've done a protocol recently, you're required to have a data sharing policy. And the thought is that unless there is a compelling reason, all of the data should be shared. So the compelling reasons include if for some reason the subject is going to, if there's a medical benefit to the subject and he doesn't want to share the data, then you can't deny them. But if it is a normal control and they don't want to share their data, then you say, thank you, I'll find somebody else. So that is kind of the established principle right now. So you need to make sure they get the language in your consent so that they are consenting to share data. There's a great website called Open Brain Consent. So if you are at an institution that has not established this language, you can go and download it and copy and paste it into your protocol. And you can point your IRB at this and tell them about all the other institutions that have accepted this language. That's not an issue at the NIMH because they have already adopted and have recommended data sharing language, and you can find all that from from whoever your protocol person is. There's an NIMH data sharing committee, so that has been working on all of those things, and that is the URL for the consent. The second part of planning ahead is when designing and collecting and analyzing your data, you should consult with standards documents. So this again comes back to the engineering, physics, and computer science community, which is something they've been doing for decades. But when you sit down to design your experiment, you need to understand what kind of experiment you're designing and what decisions you need to make, and you need to document those decisions. And there are a number of they're really just checklists. They're sort of best practices documents that sort of explain the kinds of things that you need to worry about and the kinds of things you need to document when you're doing that kind of study. One of them is Equator, Enhancing Quality and Transparency of Health Research. They have a great website. That is for all biomedical sciences. They will help you think through what kind of study you're doing. Are you doing a randomized control trial? Are you doing a matched design? Are you doing an observational study? And I promise you that your study probably fits into one of those boxes, even when you think maybe it doesn't. And it will help you think through that, and it will help you sort of think about the issues that you're going to face when you get to the analysis stage. It's very, very common in neuroimaging to collect the data and not think about what the analysis design is going to look like. If you look at these documents beforehand, it will help you avoid some of those things. And there is also a best practices document specifically for neuroimaging called COBITUS. It is available at this URL that was put together by the Human Brain Mapping community. Again, it mostly provides a checklist. When they sat down to try to figure out what the best practices are for doing brain imaging, there is a lot of disagreement. We do not yet know what the best software to use is or what the best smoothing kernel is to use. But one thing that we can agree on is that we need to document what we did. So what COBITUS provides you is some text sort of exploring some of these issues and a very long checklist of all of the things that you need to be able to know the answers to and what decisions you have made at various branch points in your analysis. And those checkpoints those checklists will help you make a better publication that thoroughly explains what you have done in that particular study. I think I have some highlights in here. Yeah, so this is exactly what I just said. Randomized control trials, crossovers, observationals, and COBITUS has 7 sections that focuses on all those different decisions that you will make during your analyses. Definitely worth reading it before you start your study. They focus on reporting, and where I really found them useful is in reviewing papers, right? So I frequently have the experience that I'm asked to review a paper and there is crucial information missing from that paper for me to evaluate it. It's very nice to say, you have not included X, Y, and Z from this public standard. Please go back to this public standard, put all this information into the paper and send it back to me. So if you can point to something that is community recognized, it's a lot easier to say, I don't know what the smoothing kernel is here, right? So you can actually register your complaint with somebody. Yeah. Again, these are mostly just checklists. They're not necessarily going to tell you how to do your analysis. They're just going to make sure that you've thought about all the various questions. The highlights in COBITUS include reporting your scan parameters thoroughly. It's all of the major scanner vendors. You can click a button and you can print out your exam card. There's no good reason not to include that in your supplementary information. That provides a full listing of everything, of all the various checkboxes that were included on your scan. It should include all of your pre-processing steps applied to the data before, and all of those should be reported. You should also report all the regions of interest and experimental conditions examined as part of the research so that the reader can gauge the degree of harking. People heard of harking? Raise your hand if you know what harking is. 1, 2, 3, about half. It stands for hypothesizing after the results are known. So you collect the data, you do an analysis that you talked about, it doesn't quite work out, and you think, oh, well, I wonder, maybe if I just split half the data and look at the male subjects, that they'll show the effect. And then you see that effect and you publish that. That's called harking. It is fine to explore your data. You just have to be clear that that's what you're doing, right? So the way that you're doing your stats, the way you're calculating your p-values, they need to include all the different questions that you have asked. Otherwise, we're just contributing to the reproducibility problem and sort of nudging our stats in a direction that is not going to lead to reproducible science. Finally, organizing your data. I mentioned BIDS before. BIDS also comes out of Stanford from Chris Gorgolewski and Russ Poldrack. It is a very simple and intuitive way of organizing and describing your data, whether it's neuroimaging or behavior. It puts it into a file structure that everyone has had to make this decision before. You've had to decide whether you're going to put your subjects over your modalities or your sessions and whatnot. This just standardizes that so that this allows developers to make it very easy to apply their tools to a new data set. And so also, if you're going to hand one data set from one postdoc to another, it's very easy for them to see what the structure is. So this is also being adopted very, very widely. And so if you're not using a BID structure already, I would really suggest that you do. It is detailed at this URL, bids.neuroimaging.io. The format was entirely community decided. There's a publication with a couple dozen authors on there, including Dan Hamwerker from here, that just sat down and said, okay, what's the best way of doing this? Again, it's open, it's transparent, and it creates a standard in which we can reuse and reproduce things. Also, so some of this can seem kind of daunting. It seems like a lot of additional things to do. And so the point of this slide is just to say you don't have to do it all at once. You can choose these battles little by little. Maybe you can share your code for this publication, but you can't share the data. Maybe the data is shareable, but the code is a mess. It's okay. You don't have to do everything. So this is a little checklist again from Brian Nozak that sort of suggests the different levels and the different aspects of open science. This is actually directed at the journals. So journals are increasingly adopting open science policies that if you want to publish there, you have to have a certain degree of transparency. But you can also use it for yourself. It's like I'm going to try to get to level 2 on open data, but at level for open code or for open papers, maybe I'm going to be at level 1 or something like that. So choose your battles. You also, sorry about the picture of Dylan there. You don't have to do it alone. We're doing a lot of training available here. So there's a couple of organizations called Software Carpentry and Data Carpentry. Their purpose is to teach you just enough computer science to make your data, to make your analysis a little bit easier. Most people that went to school for neuroscience don't want to learn how to program computers. They don't want to be computer scientists. So these courses are taught by other scientists. They will teach you, they're about 16 hours of instruction, it's either 4 mornings or 2 days, and they will give you what they have decided are the essentials for doing a more reproducible analysis. There's also the Brain Hack. So this is an organization that sort of revolves around human brain mapping. They have a Brain Hack before the HBM meeting. Sometimes there's one before the SFN meeting. There's also a global Brain Hack. Javier hosted one here on NIH campus a few months ago. This is an opportunity for any scientist to go in and interact with other scientists to sort of address some of the aspects of their analysis or their data collection that is close to computer programming. You do not have to be a hacker to go to these, and this is the thing that I hear more than not. It's like, oh yeah, I don't belong at a Brain Hack. I just feel my way around. That's really not true. If you go to the Brain Hack, there is a community of people of all levels of skill, and the idea is to help everybody move a little bit farther along. Frequently at the Brain Hack, there are educational sessions that if you don't know anything about programming at all, there will be an opportunity for you to push your skills forward. There will be a lot of experts there to talk about the different ways of doing things. So I definitely encourage everyone to get involved in either one of the global Brain Hack events or even go to the Brain Hack event associated with HBM. They're really fun, they're really communal, and I think you'll get a lot out of it. You should also ask for help. There's a lot of opportunities for this. So we are the Data Science and Sharing team. That consists of 3 people, not just Dylan, myself, John Lee, and Dylan Nielsen. We're on the 3rd floor of Building 10, and we will talk to you about any problem related to your science, especially if it's involved in trying to make your analysis more reproducible, and our door is always open. And we also run some trainings as well, including software carpentry and data carpentry. There's also a great website called Neurostars. This is kind of put together by the Brain Hack community. What's unique is that it is not wedded to any particular software package. So there's the AFNI message board, there's the SPM list, there's the FSL list. If you have a question that affects one of those software packages, you can go to those developers. Neurostars, so what is becoming increasingly clear is that the best analyses use a little bit from each of those packages, right? Some of them do things better than others, and if you're doing this for a while, you'll start to pick your favorite thing. But if you have a pipeline that's using multiple ones, it maybe isn't clear who to ask. So Neurostars is to fill that void. There's some really smart guys that answer questions there, and they will take the question regardless of what software you might be using that day. About our training, so we put on a little training back in March called the Workshop on Open and Reproducible Science. We had about 45 people and 25 people attended. We did about 16 hours of instruction and pulled in people from AFNI, from Gallaudet. We had someone from King's College, and also the BioWolf team came around. We had a lot of fun, and I think we learned a lot. All of the materials from that course are available on GitHub, so if you want to look that over. The next course is not in November. It is actually going to be in August, and we just now starting to put this together. I talked with some of these folks at HBM. So we are again going to cover Python, Git, repositories, BioWolf integration, pre-registration, and general statistical rigor. Regina Nuzzo from Gallaudet is going to come. Satya Ghosh from MIT, who writes the NiPy package. Yarek Halchenko, I think, is going to join us. He is of Debian and NiPy fame. And also Anisha Keshavan is going to be here to talk a little bit about mind control. So we don't have a registration site for this up yet, but we will be announcing it soon. Okay, so summary and take-homes. Science is changing, I think, for the better in both scope, in making things bigger, and in culture, to make things more open, to address future challenges in the way our data and our questions will be changing. Open science strives to maximize reproducibility and transparency of data, code, and papers. Adopting open science practices yields a lot of benefits in productivity, in impact, and in reach. You're going to be able to ask questions that you would never be able to ask before. You don't have to do it all at once. You don't have to do it alone. There is a lot of opportunity to help you along the path. And that's it. All these slides we put online at my GitHub repo, as well as on the fMRI website, and I would be happy to answer any questions. Yes, David.
Can I ask about the file drawer problem?
Sure.
What do you recommend that people do to help with that problem? If you have a data set that you decide not to pursue for whatever reason, what can open data help do that?
So the places that you can put data has also increased exponentially in the past 5 or 10 years, right? So there's a lot of journals now that will accept your paper regardless of whether you have a novel or cutting edge finding. So like Scientific Data or PLOS ONE or things like that. But you know, PLOS ONE will charge you some money. Scientific Data, I'm not sure if they have a fee. But what I would encourage you to do is just write up your hypothesis, do the and make some figures from the analyses you've done, and say what you expected and what you found, and put it on a preprint server, right? So then it's public. Everybody can see it. You've generated a DOI, and so if there's some other graduate student who decides to look at the same thing, they will find that if they do a Google search first. And there's nothing to say that you ever, if it really is not worth that much of your time, it never has to go to public. I mean, you can leave it on the preprint server, and that can be the final goal, but at least it's not in a dark place. It is out there where everybody can see it, and it's a relatively minimal amount of effort to get it onto a preprint server, but at least you've made it public. And then it's also citable. It's also a recent change that NIH, the extramural side of NIH is now allowing you to include preprint citations in your grant applications, which is a huge change. In the external world, people eschewed preprint service because they couldn't talk about them in their grant applications, but that's also changed recently. So it's a wonderful way to just get your ideas out there without having to battle reviewer number 3 or these. I hear all these stories about journals that just won't. The editor disappears, or they don't publish anything, and they just waste so much of your time. So the preprint servers address that. Emily?
How do you guys envision Nito working with, so like, if I'm using Nito, is that more like for collaboration within an NIMH, or is that like, I guess, opposed to OpenNeuro?
Initially, it is going to be accessible to the NIH only, but it will definitely eventually be accessible widely. The intramural program is easing into data sharing. There's some people that still have some misgivings about making things publicly available, and there will be options within Nito that you can select. What groups you want to make it accessible to. Our goal is to make things as open as possible, but sometimes that's not possible depending on what the consents are. There are a lot of very valuable data sets at NIH that were collected 20 years ago that we can't reconsent to people. So there's a limited number of people that we can share it with, but we can get it into a common structure so that the people that can access it as easily as possible. So the short answer is we'll basically give you any option of how you want to share it, but we'd encourage you to share it as widely as your consents allow.
So great talk, I love it.
Thank you.
I have a question kind of about some details that I think are actually a problem for a lot of psychologists, in that some data is easier to share than others, like resting state structural. But a lot of, I'd say the majority, at least at this point, of fMRI-related studies are psychologically based. There's a task that goes off. And we've been relating these timing files that are a big mess. So my question is, what's being done to like sort of standardize that? Because I saw the BIDS thing, and I follow Chris on Twitter. It seems to me like the BIDS is its own ecosystem. And so if you get things in that format, how do you get it back out to like programming users? Recently, I had to pre-process an AFNI, and then I had to write, actually I did an entire analysis in AFNI, and then I had to write custom scripts to get the timing files to be SPM readable.
Yeah.
So that's just a simple example of how each package has its own like issues about timing files, and it can become a mess. And it seems like that's this little detail that actually is really important for like a bulk of the fMRI community, and I'm wondering what's being done.
Yeah, so it is an area of active development. So there are increasingly, so almost all developers have agreed that BIDS is a good place to start, and people are busily writing handlers to get things from BIDS format. And as you said, in the BIDS format there is a specification for timing files, for how to specify your task and whatnot, so you can get all of the information into BIDS format. But yeah, as you said, SPM, AFNI, FreeSurfer, FSL, they all want a slightly different format to get it through their pipelines. So people are busily writing things that will move from one format to another. I'm actually kind of impressed with how quickly it's happening. We wrote a lot of them at the hackathon just this past week, but I guess the advice is hang tight, they're coming. And also, if you have done it, if you've addressed it and you addressed it programmatically, put it on GitHub. Let Chris know. I mean, even if you don't feel like it's great code, if you start it, then someone else will modify it. Like if you take a stab at the problem, tell people that you've done so, and make sure the code is available. Sometimes the best way to get a problem solved is to solve it badly, and then put that out there, and then people feel like they want to improve it, right? So we're getting there, I think, is the short answer. Okay. All right. Thanks, guys.